Welcome you all to this another interesting screencast, and the problem reads replace the loading system by an equivalent resultant force and couple moment acting at point O. This problem is coming from the Engineering Mechanics Statics textbook 13th edition by R.C. Hibbeler. We have a 3D system here with a loading system, and we have been asked to rewrite this as an equivalent resultant force and a couple moment acting at point O. Since this is a 3D problem, we are going to use the vector analysis method to sum up the forces using vector forces and also take moments about point O using the vector analysis for moments, which is the cross product. Right. So we have force 1, force 2, and we have a couple moment there. Let's start with defining the vector arms from O to each of the forces. So let's start with this one there. Let's call this as our this one, and also maybe I give this one green, or I give it red, maybe to be more visible, and the other one I give it green. Alright, so this is our R, let's call it RB. Okay, with this point let's call it B, let's call this A, and then we call this as our RA. Okay, right, so let's start with summing up the forces. So we know to say summation of forces, vector forces, will be equal to vector force F1 plus vector force F2, and these vectors we have not been given, we've just been given quantities, so we need to convert them into vectors. So let's call this point here point C, right? So we need unit vector, unit vector BC. Okay, we need unit vector which is RBC divided by the magnitude RBC. Alright, so what are the coordinates of C in the X? The coordinate of C in the X is 0.4, and then the coordinates of B in the X, we're subtracting C minus B. The coordinates of B in the X is 0, so minus 0 I. Then we have the coordinates of C in the Y is 0.5, and the coordinates of B, this is minus 4, right? Sorry, this one is minus 0.4. Okay, this is minus. Okay, so this one is plus 0.5, and then the coordinates of B in the Y is the same value, right? By J. Then plus the coordinates of C in the Y in the Z is 0, minus coordinates of B in the Z is 0.3. Let's check out. I just divide this. I divide this magnitudes, but before I go to the magnitude, let me check. So the coordinates of C in the X is minus, right? Minus 0.4. Coordinates of B in the X is 0. Coordinates of Y in the C is 0.5. Coordinates of B in the Y is 0.5. Coordinates of C in the Z is 0. Coordinates of B in the Z is 0.3. Right. So we can find the magnitude since we already know the expression is 0.4 squared plus 0.3 squared. So this is just divided by 0.5. So our UB, our UBC is just going to be equal to minus 0.4 divided by 0.5. Let me just simplify it further. So that I just want to write one expression. So this is going to be equal to minus 0.4 divided by 0.5. This is minus 0.8 I, and then we have minus 0.3 divided by 0.5. This is minus 0.6k. So this is the unit vector. Therefore, our force vector 2 is equal to F2 magnitude of F2 times the unit vector BC. So this becomes equal to 200 by this unit vector minus 0.6k. Therefore, this gives us minus 8 by 200 gives us a minus 160 I, minus 0.6 by 200 is a 120k. All right. Newtons. Let me just check it out by using Pythagoras. Okay, it's giving us 200. All right, so there we are. We found that F1 is just, this one is in it is in the along the y direction. It's along the y direction in the negative, so this will be just minus 100j. Okay, right. So summation of vector forces, which is equal to F1 plus F2, is just equal to, summing up these forces, we have F1 we said is just minus 100j plus the other one is minus 160 I minus 120k. When we sum up these forces, we'll have minus 160 I, then we'll have minus 100j, then we'll have minus 120k. So we have the resultant. So this is our resultant force, which is equal to minus 160 I minus 100j minus 120k. Alright, so this is the force system, the summation of the force vector. Let's work out the moments. So we have moments about point O. Mind you, this couple moment MC, is also going to be equal to minus, is in the x direction, is minus 75 I. Okay, is 75 I Newton meters. So summation of moments about point C, we say couple moment itself, then plus RA cross vector 1 plus RB cross vector 2. Alright, just here. I want to just put it somewhere here. Let me say somewhere here. So that I just so we have this moment vector. So we have everything. We have this component here. Then we have the force 1. We have force 1, which is here. Maybe I start with force 2, which is here. And then we have force 1, which is here. Okay, it is here. Then we have the rest, RA and RA. These are the ones I want to define right now. So we have RA is equal to this moment vector arm, which is a position vector, 0.3 k. And then we have RB, which is equal to RB, it is in the YZ plane, so it's 0.5 J plus 0.3 K. Right. Then summation of our vector moment, which is equal to the couple moment itself, summation of the couple moment, of course acting at point C, is equal to minus 75 I plus we have I, J, K, RA. What is RA? It is 0.3. And what is F1? F1 is 0 minus 100 and 0, and plus another vector moment RB. What's RB? RB, it is 0 0.5 then 0.3, and then F2 it is minus 160 right? F2 minus 160, then 0, then minus 120. Right. So let's sum up this moment. What do we have? We have minus 75 I plus I. What do we have in the I direction? It's minus, that's a plus 30, right? Minus J, 0 minus 0 is just 0. Then plus K, 0. Plus I, minus 125.5 is just minus 60. Minus J, minus 120, then minus, that's a plus, plus what? That's 48, right? 160 by 0.3, 48, right? This 0, that's 48. Yes, this is 48. This minus this, then plus K. What is K? K is 0, then minus 0.5, that's 80. Okay. Just move it a little bit like so. So once we have this, then we will say summation of this couple moment is just equal to, let's sum them up, minus 75 plus 30. This is minus 45I, and then we have no, there is another one there, sorry. There is another component, minus 75 plus 30 minus 60, that's 105, that's minus 105 I, and then J, we have minus 48 J, then K, we have a plus 80 K. Alright, so this is the moment. We have negative. Okay, let's start with the force. So the force is negative 160 in the X, negative 100 in the Y, and negative 120 in the Z. So they are all negative. Let's try and show that in 3D. Let's imagine we have something like this, or maybe this one, maybe up to somewhere there. X, we are assuming it's a bit bigger. Alright, so let's say something like that. Alright, so let me just create some dots. I clean it up I clean this one up. Okay, so let's say this is our point here. So let me use red. So we can say this is our resultant here. I mean our resultant force. And this resultant force is equal to minus 160 I minus 100 J minus 160 I minus 100 J minus 120 K. Okay, there we go. So Newton, like so. So that's our resultant force. Then let's say our moment, we have 105 in the Z, I mean in the X, and then minus 48 in the Y, and the other one. So we have negatives. In both X and Y, and then we have a positive Z. So this one we can just assume without really showing that. Let's say it is 105. Where is it? We have a higher value. Maybe we say something like this. 80 shorter value. 80 shorter value. X. Alright, let's just put it something like this. This is just an approximate. These are not exact values. They're just showing the would-be direction. Okay, so that is our moment. So we have 105 I minus 48 J plus 80 K. Okay, so Newton meters. Right, I think this is about it. I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, see you in my next screencast.